to London Underground and how their signalling system works, and then looking a little bit more to the future to CBTC and modernisation of the tube. So who am I? Well, I've been around a long time, for 43 years now, nearly 44 years in the industry, actually, starting in 1977 as a trainee technician on telecoms side rather than in signalling. But I suddenly found that wasn't particularly exciting, so I decided to move over to the signalling side pretty early in my career in 1978. I went into the design office, and I worked in the design office worked through my grades in there, from sort of junior grades up to a slightly more senior designer. And then decided to move into testing and commissioning. I'd liked testing and commissioning. I'd been doing a little bit to help out at weekends and so on, and earn some extra pocket money. So I moved into signalling and into testing, and thoroughly enjoyed that. And eventually became the testing and commissioning engineer for British Rail Midland Cross Country in Derby in April 1994. 96 saw a lot of change in both my career and that of many other people as we went through privatisation, and we ceased to be British Rail anymore, and became private companies. Me coming into Balfour Beatty. That changed again in 2007 when Signalling Solutions was formed, which was a joint venture between Balfour Beatty and Alstom, and we formed a new company for delivering signalling projects across the UK. I became the engineering director of that company. Finally leaving there to go and become the head of signalling at Parsons Brinckerhoff in 2012, which is quite a changing job. I ended up going there and working on HS2, developing some of the early interfaces with Network Rail. So then I left Balfour Beatty because Parsons Brinckerhoff was part of Balfour Beatty, so I left there and joined Atkins as the head of engineering management, and then carried on with other jobs in Atkins. Not because I was good or was getting better, but basically because there was a lot of reorganisations. So I had a lot of jobs while I was working there. Probably the most interesting one of those was technical director of future signalling systems, where we were developing some new interlocking technology called the Atkins signalling method, which sits around an electrologics interlocking. And we commissioned the first one of those not long before I left there. So I retired in January 19 and took part of my pension. But just prior to that, I met a man in a pub, as they say, and he offered me a job to come back to Balfour Beatty. They were setting up a new signalling division, and was I interested in helping to do that? So I thought about it, and then thought, yeah, go on then. So I thought it'd be a sort of an easy job to ease into retirement, which proved to be very untrue, but there you go. And the rest of the say is history. So here we are. So a little bit of history then. So there's a saying here that was by Richard Christopher Rapier from the Institution of Civil Engineers, that basically said that the laws of nature, you should prevent two solid bodies being in the same place at the same time. And effectively, that's what we do in railway signalling. This axiom is still very true today, that basically our aim in railway signalling is to prevent two bodies being in the same place at the same time. So the primary objective of the signalling system remains exactly the same today: to prevent collisions between trains. So I was meant to switch off my did you see the message come in then? Let me just shut down email. That's probably the easiest thing out. You didn't see that come in? Oh, okay, that's fine then. Okay. Yeah, to prevent collisions between trains, to maintain a safe distance between following trains on the same line. So that's something that some people sometimes forget about, is that we need to stop trains running into the back of each other as well as meeting each other at junctions. To safeguard the movement of trains at junctions and crossing the paths of others where you've got points or crossovers or anything of that nature. And to prevent derailment of trains at incorrectly set points or inadequate lock facing points. So points these days with machines on them have the locks built into them, but in days gone by, a lot of points were just free to move, and of course that created accidents. So eventually there was facing point locks put on them so that you could actually lock the points in position, which stopped a lot of that happening. And finally, to regulate the passage of trains according to the density and speed required. So one of the other things that we do, if it's a high intensity railway like London Underground, we need to get the trains as close as possibly can do to each other. If it's a more rural railway, then we signal it appropriate. There might only be a train an hour or 2 or 3 trains a day even. So we do the appropriate signalling for the situation that occurs. So it all started with the time interval system, and we had signalmen, or they were sometimes called policemen. Well, they were policemen. Sometimes they were called bobbies. And funny enough, that term remains even today. If you go into a signal box today, you can still refer to him as a bobby. It's not an offensive term. It's a term that they quite endear to. So yeah, that still sticks. So they would give a clear signal to a train if the first train had passed by a greater than stipulated time. So you had a man standing on the ground effectively where the train was. He may have had a signal that was operated from where he was standing. He would have a stopwatch. And once the train had gone, a predetermined time would be established, 5 minutes, 10 minutes or whatever. And once that had passed, then he would let the next train go. The trouble with the system is he didn't know whether that first train had got to the next station or not, whether it successfully managed to complete its journey. And obviously we're talking early days of railways here. There were a lot of breakdowns, things were unreliable, locomotives weren't quite what they were today. They'd maybe run out of fire and then run out of steam. So it was a little bit haphazard. So if the first train stopped on the route, then the idea was that the guard would get out of the train and he would walk backwards displaying a red flag, so that if a second train did come, the driver could observe the red flag and would stop. So in theory, 2 trains couldn't run into the back of each other. But as I say, it's the theory. It certainly wasn't the practice. Trains also had very poor braking systems. Often the only effective method of braking was to put the locomotive in reverse. They didn't actually have brake blocks or anything akin to that on the wheels or disc brakes as we have today. So literally they'd be trundling along and the driver would put it into reverse to slow the train down or stop it. So between 1830, which is really when the railway sort of started to develop, and 1889, there were many accidents. So in that same period, from the 1830s through to 1889, the first fixed signals began to replace hand signals worked by the policemen. So we were now seeing structures being put up, simple structures in those days. Sometimes different companies did different things. Some would raise a ball up the post to say that the line was clear, and lower the ball when it was occupied, or vice versa. Very much a sort of navy type system. And then some of the signals had swinging bars on the top of them, which were out of view when the line was clear, and sort of right angles to the railway when trains couldn't proceed. So eventually that sort of came to where the signals were grouped into cabins, or what became known as signal boxes, rather than having a number of bobbies out on the track at different signals. If it was a sort of relatively complex layout for the day, what they would do is they would group the levers together so the bobby could be in a sort of hut, or it wasn't much more than a garden shed in those days, but at least they were all grouped together, and you could do away with some manpower and keep the man in the dry. So then in 1837, the telegraph was invented, and that gradually began to get rolled out to the cabins so that they could communicate with each other. And this meant now that the time interval system could gradually be done away with. They invented a system of bell codes between the signal boxes, which enabled the signaller receiving or the signaller sending to understand whether the line was clear or whether the line was occupied, and then allow the train to go accordingly. So that made things a lot safer with using the fixed block, and that was introduced mainly between the 1850s and the 1860s. So in 1889, the Regulation of the Railway Act was put in place. This was colloquially known as the Lock, Block and Brake Act. And the reason it was called that was because of what they were doing of locking things together, putting a fixed block system in place, and making sure that trains had continuous brakes. So it became known as the lock, block, and brake. This it followed a series of more serious accidents. Obviously, as trains were getting bigger, they were getting faster, they were getting more of them. So the accidents, when they occurred now, were getting worse, unfortunately. So the Armagh disaster was one of the accidents that really provoked some serious change. 79 people were killed in that accident, many of which were school children. It was a Sunday school outing. The train had pulled out of Armagh. I think they were going off to the seaside, and because there were so many people on the train, the locomotive wasn't capable of getting up the hill, so it stopped. They split the train in two. The front half of the train with the engine went off to the top of the hill, where the idea was the engine would come back and pick up the rest of the coaches. But unfortunately, the only way they stopped the train from going down the hill was to put stones under the wheels. And with the movement inside, with the excited kids and all the rest of it, eventually the stones crumbled and the train ran away and ran into another one coming up the hill from Armagh. So that was one of the worst disasters. In fact, it was the worst disaster in the UK at that time, and it remains Ireland's worst train disaster to date. So fixed block signalling became compulsory on passenger railways as part of this act. So no more time interval system. Basically, between signal boxes now, you could only have one train, and that reduced the risk significantly from that point on. It also introduced interlocking between points and signals. It was required that where points allowed you to move from one line to another, that movement would be protected by signals, and those would be locked together. So now we were seeing that the shed where the bobbies were standing would now start to resemble more of a signal box that probably some of us have worked in over the years, or certainly seen pictures of. And it became more sophisticated, with locking bars between the levers, big lumps of metal, still not that sophisticated, but it still serves purpose today in many places, particularly abroad, but there's still quite a lot in this country. And it also introduced continuous automatic brakes on trains. So now if a train did split for any reason, or had to be split for whatever reason, then the brakes would automatically be applied as part of the automatic brake system on the train. So that was the Lock, Block and Brake Act. The two other things that the Act introduced, which we probably all wish it hadn't, was a requirement to print the fare on every ticket. So now you couldn't just get a ticket for any old fare. It had to be printed on the ticket, which meant that companies had to set up a fare structure. And it introduced penalty fares for not having a ticket. So we moan about penalty fare zones today, but it's nothing new. It was actually put in the 1889 regulations of Railways Act. So there you go. So, oh, that's interesting. Can you see the railway line on that? There's no railway line. I don't know what's happened to the railway line. It's shown on my lower slide, but it hasn't come up on the screen for some reason. That's very interesting. Doesn't bode good for some of the others coming up. But imagine that there's a railway line. Just I don't know why that would be. Very strange. Some of the lines haven't shown up. So basically what I've just been saying there, we have the three signal boxes, we have three sets of stop signals, what's commonly known as a home signal and a starter signal, and between those signals we have station limits. So the signalman at that point can do anything that he wishes to do. It's his area to control. There's no need to receive any permission from anybody else. So there's three sections shown like that on there, and then in between those there is a block section, which is the piece of railway that he needs to have permission to go along. So if a train wants to proceed from signal box A to signal box B, then the signalman at A would ask B whether the line is clear, i.e. the last train has arrived, it's inside his station limits, the line is clear, safe to send another one. He could then clear his signals to send one through. And similarly, when B wants to send one on to C, the same thing again. He would ask whether the line is clear. Assuming it was, he'd be allowed to clear his signals, and the train would go on. Eventually, even those signals between the signal boxes were linked, and you couldn't clear the signal into a block section if the last train hadn't arrived at the next box safely. So gradually these controls got more and more sophisticated as time went on. So the issue with what you've just seen is the fact that there's no the stop signals are stop signals. So basically, a train proceeding from one signal box to another, the first thing he would come across would be the signal at danger if it hadn't been cleared to proceed through. So he received no warning. Now that's all very well and good on a bright sunny day, but if it was nighttime or it was fog, then judging that where that signal is and the breaking point to start slowing down for that signal was very difficult. If it was raining, obviously it'd be similar, and so on. So eventually distant signals were introduced. These started to come around from the 1870s and were slowly introduced by most railway companies. They looked a little bit different across the different companies, but essentially they were placed to warn a driver that he was approaching a stop signal. It was recognizable from a stop signal because it was a different color and it had a fishtail arm in the end, and it also had a light in it. Now they put a light in which in those days would be oil lit, today would be electric lit or LED lights or whatever, but the yellow light would be shown for caution or the signal being on, and a green light would be shown if the signal was off. That's a slightly different color to a home signal. A home signal would have a red for being on and a green for being off, and so the yellow was to distinguish. It matched the yellow of the arm. It just was to make it look different to the home signal. I'm going to have trouble here. For some reason, it's not displaying some of my lines, and I'm just wondering whether the graphics will work. But we'll see what happens. Yeah. So looking at the scenario here now, we've introduced a distance signal. You can see the block signals there between the signal boxes, the home signal, the distance signal. So what would happen if a train wanted to go through from one to the other is that first he would clear his home signal, which would allow the train to proceed up to his starter. He would then clear his starting signal. And at this point, then the line is now clear for the train to proceed. But if he was coming from beyond box A, then he would clear his distance signal as well, and the train would go through as such. So stop at the home signal at the box B, he would clear that and allow it to move up. And if he got a line clear to the next box, then his signal would clear, and away he would go again and off to the next section. So. So that's how trains were now signalled through the system like that, and then the signals would be put back on again by the signalman, and the process would be repeated for the next train. So what I thought, being as we've looked at the history, probably now was quite a good time for the quiz. So if I hand back over for the quiz, and then we'll come back and we'll carry on after the quiz.
Perfect, thank you. And I'm going to share my screen. Just let me know if you guys can see it. Can everyone see that okay?
Yep, I can.
Yeah, perfect. So yeah, the usual Kahoot quiz on these knowledge sharing sessions. So if you can all log into kahoot.it, and I'll just share the game pin as soon as it loads. So if you go to kahoot.it and then just put game pin, which is 1720664. I'll give it a minute or so, try and get, I don't know, let's say 15 players if possible. So if you can join, please do. Thanks, Ref, Elvis, C, AB. Oh, they all come at once. Here we go. It's also a pretty varied quiz, if I can say that. So I hope you enjoy it. We'll just give it a couple more seconds.
Pradeep is normally the man to beat on these things, isn't he? Although I think Chaz smoked him on the last one.
He did, yeah. Chas, Pradeep, and Aman, actually, they're the ones to beat. Are you not joining, Damo? You haven't seen this either, have you?
No, I'm trying to concentrate on the IT.
Yeah. All right, we've got 13. I'll wait for one more. Yeah, perfect. Okay, I'll start. You guys can keep joining in as we go. But yeah, so welcome to the knowledge sharing quiz, first session of 2021. Hope you enjoy it. So the first question is, what percentage of the river Nile is in Egypt? Is it 22, 50, 85, or 100? Got 10 answers in, 10 seconds to go. A bit of a tricky question as well. So here we go. Only 3 got it right. So the correct answer is 22%, which is actually a pretty surprising fact. Jan is in the lead. Well done, Jan, with 808 points. Question 2. What is the only major city located on 2 continents? Is it Istanbul, Vatican City, or Monaco? Again, a pretty tricky one. 13 of you got that one right. It is Istanbul. I didn't actually know that, so well done all. Jan is still in the lead with Connor and Basu in second and third. So question 3 is guess the flag. So simply guess this flag. Is it Estonia, El Salvador, Botswana, or South Sudan? 12 answers in. Wait for one more. You got 3 seconds. The correct answer is Estonia, and 7 of you got that one correct. Let's see. Oh, Connor and Raf in first and second now. They've made a lead. Question 4. Again, guess the flag. So, which country's flag is this? Is it Haiti, Venezuela, Ecuador, or Colombia? I tried to make them a bit more difficult this time. 12 answers in. Let's see, it is Ecuador, and 6 of you got that correct, so well done. Chaz again, straight into the lead with Jimmy in a close second. This is a music round. So what is the Beatles' first album? Is it Please Please Me, Abbey Road, or Revolver? It is, in fact, Please Please Me. 6 of you got that correct. Chaz still in the lead with Raf and Jimmy in second and third. So question 6, which Canadian artist released Man, I Feel Like a Woman in 1999? Was it Drake, Boy George, Michael Jackson, or Shania Twain? "15 answers in. And yes, 9 of you got that correct. It is Shania Twain. I'm hoping I'm saying that correct. Chad's still in the lead with Raf and Jan in second and third. Question 7 is movie posters. So which movie is this poster from? Is it Up, Alien, Predator, or Survival? It is Alien, and that was quite an easy one. 14 of you got that correct. Chad's still on fire with Raf and Connor in second and third. And the final question, which movie is this poster from? Is it Terminator, Walking Dead, or Dirty Harry? It is Dirty Harry, and 12 of you got that right. So let's see who's won this session. In third place, we have Connor. Well played. And in second, we have Raf. Well played as well. And in first place, I'm guessing it is Chaz. Again, the one to beat. Well done, Chaz. So I'm going to hand this back to you, Ian. I hope everyone enjoyed that. And yeah, thanks for playing.
Okay. I've gone back to the start. Thought it would. Just bear with me.
No worries.
I just wanted you to see that little train go across the screen again. There we go. Right. Everybody see that okay?
Yes, yeah.
Good, excellent.
That's fine.
So let's have a look at how this is applicable to London Underground. Now, obviously, what we've been talking about up till now is very much a piece of history. Systems like that still do exist. There's still quite a few in this country, although they're slowly disappearing now. But London Underground very much uses colour light signals, partly because it is underground and partly because the system is more modern. There were originally some semaphore signals on the first underground lines, but fairly quickly they became electrically operated. So there's sort of two sorts really. On the left group there, the left group of two signals, you can see is they're automatic stop signals. So they're plated with an A, and they show red or a green. Next to them we have repeater signals, which are plated with an R. We don't have those everywhere, but again, like in the distance signal in the previous examples, these are used to warn the driver of the aspect of the signal ahead. It may be that there's a curve, it may be that there's poor sighting of some reason, and you can't actually see the home signal, the stop signal, so we provide a repeater signal. In some circumstances where signals are very close together, we actually combine those and you get a combined automatic stop and repeater signal. And you can see that apart from the center one there, they're showing two aspects. The reason the center one is only showing one aspect is because if a signal of that type is showing red, we don't show what the next signal is showing. You just get the one aspect. That is to eliminate any confusion for the driver, because he might not understand that the repeater signal underneath is telling him of the next signal. So we just give him a red. Red means stop, and that's it. That's the only information he gets. But if that signal is showing a proceed, as in the left one and the right one, then we can show him underneath what the state of the next signal as well is by the repeater signal. And the one on the right is a controlled junction signal. So this has three white lights, slightly different to the mainline railways. On the mainline railways, we have 5 white lights, basically because we're talking normally anyway, talking of higher speeds, so it gives better sighting to have the 5 white lights. So that's just the worst signal. Some signals on the mainline railway did just have 3, but all these days have 5. So signals used to control the safe movement of trains. We've talked about that previously. And in most UK systems, the signal only tells the driver the state of the line ahead. His route knowledge on what he has learned when he was training to be a driver tells him how fast to go. So this is actually called route-based signaling. He knows, he learns from books, from practice and all the rest of it. He knows how to drive on that piece of track. He knows how fast he can go. The signal just tells him whether to proceed or not to proceed. On the continent, continental Europe railways, though, and other places in the world, a lot of it is speed signalling, which is a little bit different. And the signals look very similar, but in this case, the driver is told the maximum speed he can go, but not where he is going. So this may be through, in some systems, you actually have a number. So you put a number up, which it may be, say, I don't know, 15, which might mean 150 kilometers an hour, or it might be a 10, which is 100 kilometers an hour, or sometimes it's the combination of aspects of the signal as well. So you may get 2 greens, which means whatever to the driver, whatever the speed he can go. He might get a yellow over a green, which means he can go slower. So that's known as speed signaling as opposed to route signaling. But virtually everything in this country is route-based signaling. Signals approved are light. That's quite an important development that took place many years ago now, so that if a signal goes out, the signal behind cannot clear. So it's a safe system. It means that the driver isn't coming up to a signal that is out, and he wouldn't know whether it was supposed to be red or whether it was supposed to be green or yellow or whatever. So we actually prevent a train approaching a signal that isn't lit. That doesn't happen so often these days because we're using LED signals now rather than filament lamps. Filament lamps did develop over the years. Originally they were single filament, but then they became double filament, so that if the first filament went out, you got a second chance. And that then also warned the technician at the time, so the technician would go out and replace that lamp. So there was even filament lamps got quite sophisticated, but the vast majority of filament lamps now are being replaced by LED types. In fact, we're undertaking a contract at the moment to replace all the signals in the London Euston area with LED types. That's one of the big areas on the West Coast at the moment that still isn't fitted. So that makes them even more reliable from then on. And the aspect of each signal can be repeated to the signaller. It depends on the system that we're using. Sometimes more information is available than others. On more modern systems, we can actually show the signaller exactly what aspect is being displayed. On some of the older systems, we can only show him whether the signal is at danger or is a signal proceed. It just depends on the vintage of the equipment. So again, for some reason here, we haven't got the horizontal line, we haven't got the railway line. So you just have to imagine that there is a horizontal railway line there. And this time I've converted it from a steam train because we're now running underground, so it's now an underground train. And you can see there that the distance signal, the repeater signal is at green and the home signal is at green. But the next pair, the home signal is at red, therefore the distance signal is at yellow, warning the driver that he's coming to a stand. So what happens is, all being well, so you have to imagine it's running on rails. So that's how the sequencing works on the underground, and you can see now that both of those signals are at red and both of the distance signals or repeater signals are at yellow. So we've talked a little bit about signals now. Let's move on to thinking a little bit more about how we tell where the train is. And we tell where the train is on certainly older systems. We're moving more now towards actual counters, but in the true vein of working our way through the history of the system, trains were until not too far in the past actually detected by track circuits. So they're formed of they're a vital component. They're actually a lot of people think the track circuits are there to detect that where the train is, but the reality is that the track circuit actually tells you that where the train isn't. Because a track circuit can fail. If a track circuit fails, it goes occupied. That is exactly the same situation as if a train is on it. So we don't actually prove that there is a train there, but we do prove that the track is vacant if the track circuit is showing clear. So that's quite an important point, that second bullet point. And they're normally, or often I've said, they're defined by insulated block joints. There are different sorts of track circuits. The ones used on the underground are mainly one particular type, so we would define those with using block joints. But more modern track circuits, they don't need block joints, which makes it easier for P-way design, easier for maintenance and so on. The track circuits that are used are mostly AC track circuits because the traction current is DC, and they have to be immune from that. If the two were the same, so they were both DC, what you'd find is that the interference in the system could be sufficient to make the track circuit relays operate when trains are actually present. So we use a different sort of track circuit depending on the traction. If you've got AC traction, we tend to use DC tracks. There are some track circuits that will work on both railways. They're immune to both AC and DC traction, and they can be used in certain circumstances as well. They only use very low current track circuits. You wouldn't generally speaking get an electric shock off a track circuit. They're usually very low voltage, typically for a DC track circuit, around about 5 volts or so. AC track circuits can be higher, and they can give you a bit of a tingle if you touch them, or if you short out a joint or something like that, but it's not going to cause you any serious harm. And they use very low currents as well. So obviously we have to protect them from the massive currents that are flowing in the track used by the trains. So the components of a track's AC track circuit, that is essentially what it looks like. Excuse me. You can see that on the left-hand side, let's take a glass of water. On the left-hand side, we have the track relay. On the right hand side we have the track feed, so power comes in from a source at the top, goes through the various components into the track, flows along the track, and then goes into the relay, and the relay can tell the interlocking whether there's a train present or not. So in this case we have the direction of travel is from left to right. That's the train detection relay. It has 2 coils in that, one coil that's operated by the current coming through the track, and one coil that is the local coil, which is connected to 110 volts AC supply. We have fuses, which is to protect the equipment from the high currents in the track. If something was to go wrong, we'd rather the fuse go and the track circuit fail than the current get into the relay or the feed and literally blow things up. I mean, they do literally blow up if things go wrong. Isolation transformer, which isolates the supply coming in from the feed end, so that every track circuit is independent of every other. They're not all wired together from a power supply point of view. A variable capacitor that is used for changing the frequency in the changing the phase angle in the track circuit between the current and the voltage, to give you fine tuning to make sure that your relay operates correctly at the other end. As I say, this type of track circuit is defined by insulated block joints. So in this situation, we would have an insulated block joint in one rail at either end of the track circuit to define it, and then there would be another track circuit connected the other side of each of those block joints, and so on and so on. So we have the continuous rail, which is for the traction return current. There's no insulated block joints in that. That allows the current to flow back from the train. We have what's called the section rail there, which is the one with the insulated block joints in. And when the track circuit is clear, we have this situation. Not sure how well you can see that, but the current flows down through this circuit here into the rails. It flows along the rails, back up here into the one of the coils of the relay. The other coil is energized through the local coil, and we have here, as part of this relay here, we have a number of contacts, and in this particular case I've shown 2 contacts, which has got a 110 volt feed on it, and you can see that the contact is closed, so that feeds off to the interlocking, and the signal sits at green. There's no train there, the track circuit is clear, the signal is green, the contacts are made, a train can move along. So eventually the train comes, and what happens there is now it has shorted out the track circuit, so the current is still flowing through here and coming into the rails, but the wheels of the train, the axles of the train, are shorting out the current now. So in this case now, no current can flow through into this coil here. With no current in there, that relay then drops, and when that drops, these contacts open, and you can see now that there's no current flowing through either of these contacts, and so the signal goes to red. So that's the basic philosophy behind how the track circuit works. So many different variants on that, and it can be done in many different ways, but that essentially is how the AC track circuit works. So monitoring track circuits, in modern systems, they can show when problems have been occurring with track circuits. So we can determine when a track circuit is showing occupied when it should be clear. We can look at sequences of track circuits as trains go through, and if you get a track circuit occupied, another track circuit occupied, but the first one doesn't then clear when the train goes, the system can actually monitor to make sure that we understand that track circuit should have cleared, and it probably isn't actually a train there. And the various rules can be implemented at that point. Something can be inspected, and then the trains can possibly still go through, depending on local operating rules, even though that track circuit is showing occupied, because we know that there is nothing in there. We can also tell where trains shouldn't be, but I'm not sure whether there's much of this on the London Underground. I would imagine there is. It's something I'm not sure of myself, but certainly on the main line railway, we now have quite sophisticated what we call SPAD systems. SPAD is a signal passed at danger. So as soon as a train passes a signal that it has no authority to do so, it has no movement authority, what happens is the SPAD alarm system picks this up. In the most sophisticated systems, it puts all the signals in that local area to red, so that if there's any other trains approaching, then they are stopped, and hopefully any sort of incident is avoided. Track circuits can also suffer problems from dirty rails. Not again so much on the underground, because although we do get water down there at times, it's generally a sort of fairly clean environment, and the rails remain shiny. But on the main line railway, quite often we get dirty rails when the trains are infrequent, and particularly actually after engineering works as well, where maybe no trains have run for a whole weekend. Then you can get dirty rails, and you have to be careful when the first trains go through to make sure that they are detected properly. And OBB, one of our sister companies, obviously, they produce monitoring systems, and they can be programmed to detect these types of errors and raise alarm to either engineers or to signallers. And there's a number of, well, there's actually hundreds of these systems being implemented at the moment, all up and down the East Coast Main Line. A massive contract for providing these systems, and that's probably the subject of another talk on another day. So to the future, the underground is being modernised. As we all know, 4-line modernisation is well underway for the Circle Line, the District Line, the Hammersmith and City and the Metropolitan lines. And the 4LM project actually represents about 40% of the network mileage. I'll show you on the next slide in a minute where it actually runs, but it's obviously a huge part of it. Work began on that in 2016 and is being rolled out now. Parts of it have been changed over, and it uses the Thales Communication-Based Train Control System, or CBTC, and their company name for that is called Celltrack. And Celltrack, some of you may recognise as being a very similar system to that used on the Docklands Light Railway. To manage all of this, a new control centre is being built at Hammersmith, and it will control the CBTC system for the 4LM. So 40% of the network will be controlled from one signalling centre. The trains will be driven automatically. There will still be people in the cab, much the same as there has been on the Victoria line for many, many years. Automatically. And this is similar technology to that that's already been introduced on the Jubilee line and the Northern line. The software being used in this system, though, is slightly developed beyond what was included in those. And there you can see a map of the 4LM system, and certainly from the west to the east is a long way. You can't really see it on this scale, I don't think, here, but that line there is 4 miles. So if you imagine that laid on top of there, it's a long distance from one end to the other, a good number of track miles. So some new concepts are being brought in by the modernisation, and I just thought I'd mention one or two of those to you. You may have heard things about them in the past, and they've not meant anything. So CBT system provides automatic train operation, as I've said. So we call that ATO. It provides automatic train control, which is ATC, and automatic train protection, which is ATP. Now they're all subtly different. They're all about driving the train automatically, but they have slightly different roles to play in that driving. So ATO can have a varying degree of automation. Now the 4LM we have what they call the grade of automation, GOA 2. So that is where stopping and starting is automatic, but a driver is required to operate the doors. And if there's any emergency happens, then he controls that emergency as well. So there's still effectively a driver on the train, but he doesn't normally drive the train. GOA 3, that steps up to where there is nobody in the cab, but there is somebody on the train, let's say a train captain like there is on Docklands, who is capable of taking control of the train, but doesn't normally sit in a position where he's driving it. And then finally GOA 4, which is the highest level, where there isn't actually any operator on the train at all. The train just operates totally autonomously. If there are any emergencies, then that they have to be dealt with outside of the train. People have to deal with that either in a control room or on a station or whatever. So there's varying degrees of automation. As I say, 4LM will be GOA 2. So looking at ATC then, ATC is how the train responds to external inputs from the signalling system. So when the signalling system says to the train, right, I want you to speed up or I want you to slow down, that is done by the ATC, and it also controls where the train stops. And probably an important factor is that it will apply the brakes at the maximum speed of the train. So if the maximum speed of the train is 100 kilometers an hour, when it gets up to 100 kilometers an hour, then the ATC system will apply the brakes at that point to stop it going any faster effectively. And then ATP, which is the final part of it, this protects the train, applying the emergency brake when the speed permitted by the signalling system is exceeded. So this is not quite the same as exceeding the maximum speed, the 100 kilometers an hour, but if there's a point on the railway, for sake of argument, where you have to slow down from 100 to 60, if the train doesn't slow down to 60, then the ATP will take over and will make sure that that train is brought under control, and usually to an emergency stop. So the other thing that's happening is the introduction of moving block. I talked early on about the fixed block system. We saw the signal boxes where you have a piece of clear track between each of the signal boxes, and only one train is allowed into that block at any one time. Now that block is fixed depending on where the track circuits are, how long it is between the signal boxes, and so on. You can't change that. But with CBTC, we have a system what we call moving blocks, where effectively the train itself becomes the block now. So rather than having a fixed point for anything to happen at, then those blocks move along with the train. So each train is in constant communication with the signalling system using fixed aerials in the tunnels, and that system knows exactly where the front of the train is and where the rear of the train is. So they can actually get closer together. So just like cars on a road, the slower that it's moving when you're driving, if the road is congested and you slow down, you obviously get very close to the car in front. But if you're on a motorway driving at 70 miles an hour, at least anyway you should do, you should be driving a lot further back from that car to give you time to stop if the one in front stops. So it's a very similar system to driving a car. The only difference is that there is a small safety margin built into this, because obviously we don't want one train to stop immediately at the back of another train, because if that was the situation, you only need a little bit of greasy rail or something like that, and all of a sudden you've got one train colliding with another. So again, unfortunately, I do apologise for some reason why my horizontal lines are not there. But here's a demonstration of what I'm saying here. If we take conventional signalling, the train comes through and stops at a red signal. Once that has happened, then a second train can come up behind it to the next red signal, but we're now fixed how far that train can go. We can't actually move that train any further on than that. That's as close as it can get. But with CBTC, our first train comes in and stops at a stopping point, and then the next stopping point is established based on where the rear of that train is. The next train comes along and stops at that stopping point. We can now establish a third stopping point, and the next train comes along and stops at that stopping point. So you can now see that in more or less the same distance there, we've now actually got 3 trains rather than 2, because in the CBTC system at the bottom, they can get a lot closer together than they could on the fixed block signalling at the top. So some advantages and some disadvantages. Advantages, there's no more line side signals, so there's less clutter of cables. When you're relaying, they don't need reconnecting at the end of the job and testing. Train stops are not required. Costly mechanical equipment, again, doesn't need putting back after a relaying job. Track circuits are not used for train detection, so there's less cables for those as well. So again, we don't have to worry about running those in at the end and getting those tested. CBTC provides additional capacity, believed to be around 33%, as the trains are not kept apart by the fixed blocks that we described in the early part of the talk. I say believed to be because it can vary depending on the particular circumstances, where your platforms are, line speeds and all those good things. But so if we assume sort of around 33%, and the slower the train is moving, the closer it can get to the one in front. Some disadvantages, though: the trains have now become very complex. A lot of signalling equipment now goes on the train rather than on the ground, so the trains themselves have become very complex. The system integration and testing takes an awful long time when a new train is introduced. The underground trains for 4LM have all had to be tested out at old, make sure that all the technical systems work. And unlike mainline railway, CBT systems tend to be more bespoke. There's no such thing really as a standard CBTC system. So just some final thoughts. Each train transmits its position from an aerial to a few centimetres. The system knows where the train is to a few centimetres. Trains receive movement authorities from the interlocking to tell them how far they can go, and that's known as a limit of movement authority. And the target speed is set to 0 at the end of that target end of movement authority, so the train will always stop at 0 speed at that point. Much of it's IP based, making it future proof, so we can rebuild parts of it with new IP based equipment. You don't have to replace the entire signalling system. Maintenance costs can be reduced because there's less architecture, and high levels of reliability and availability can be delivered by the system. So what have we learned? Well, we've learned about fixed block systems, keeping trains apart. We've learned about how fixed blocks work on older underground lines, but how track circuits worked. And finally, we learned about CBTC and how it increases the capacity. We can get more trains through the system, and that's going to be the way that ultimately the whole of the London Underground will work. So thank you for listening. I hope you found the talk useful. And if anybody wants to ask any questions, I'm happy to hang around.
So I'd say that was a brilliant presentation, Ian. Thank you very much. A couple of things that you hit on there. Just towards the end, you were saying the signal systems on the trains are very complex.
Yep.
A recent project that we done at Queen's Park. I was hoping someone would be on here from Signals. I don't think there is. So I don't like to put you on the spot, Martin, but I see Martin Broughton in the chat. So Martin might be able to give us a bit of detail in it. So we handed the site. We were working on a site at Queen's Park. We handed it back on time. Everything, as far as we knew, was good. We handed the work site back to the Peter Wilmsey, was the possession planner. Give it to him. We all went home. Everything was hunky-dory. But the next morning, the trains that had left site, because the route back to Ruislip took them across lots of different signalling systems, there was they had to go through a lot of different areas, and he had a nightmare getting trains out and getting them to connect. I'm not really, so Martin, you might be able to tell us. I don't understand a lot about it, but I know that the trouble getting the trains out, I'm not sure if it was service, Martin, but I think it was to do with the train communicating with the various track bed assets, wasn't it?
Thanks, David. First of all, Ian, great presentation, thoroughly enjoyed it. So I've had a lot to do with TBTC and CBTC, not in the operational sense, for quite a few years actually, and the risk always seems to be the interface between one signalling system and another. So when you're crossing from legacy Tripcock signalling onto either TBTC, CBTC and back, there's a bit of physical kit on the train. It's referred to as a latch relay the relay's got to go across.
Yeah.
And that's a straightaway vulnerability. You've also got operational vulnerabilities with drivers not knowing that they're at the boundary and taking the right action. So first of all, migrating across one signalling system to another is an inherent risk. Also, if you look at let's say TBTC, you've got a Jubilee line train that's 117 meters long, I believe it is. It's fixed. It's 7 carriages. It's hardwired. It's got a vehicle on board computer in the front cab and in the rear cab, and it's able to work off either. And the signalling system knows where both VOBC is at any time. And let's say if it goes down to 1, that's fine. The other one takes control. With an engineer's train, they're not fixed length. So we run quite short trains. We run 2 locos to Hainault to recover trains during the week, and we run nearly 139 metre trains. And because we use mixed wagon stock, we have to uncouple and couple them up, unlike passenger stock. So therefore, you can't hardwire the front VOBC and rear VOBC. So Tullis had a lot of problems, and the decision was made that we treat an engineering vehicle, for the sake of complexity getting the project over the line. We make a hybrid VOBC into engineering vehicle for the system, and it's the longest it can possibly be. It's the slowest it can possibly run at. It's got the worst braking capacity because it's the heaviest it could be, and worst of all, it can only run off the front VOBC. So the rear one is kind of almost a complete passenger. Mm-hmm. Then you've got interfaces between the Bakerloo and the Jubilee where no passenger trains run, and so you're making a move which involves 2 line control departments, 2 signalling systems, and trains that don't normally cross the 2, and the same at Neasden to the Met. And inherently, that's the problem. So we've also got 29 battery locos on the transplant fleet, and we've got 18 last time I was told fully converted and commissioned with TBTC. They will all be fitted with CBTC by the end of the project, but it's not done. The same with Tempers aren't done. So now you've got a bunch of fleet drivers with a regular knowledge because they don't use it very often, and you've got the signalling systems not used to being crossed over. And that's broadly speaking the issue. I think we had other issues, outside issues, with staff thinking they knew how to fix the problem rather than moving the train, and that's both an operational and a maintenance issue. We know that's the vulnerability. And the other thing I'd just like to say is generally, when you've got service trains, they sit in depots and they're not normally in the system, but they go to the entry, the migration point, to enter the TBTC or CBTC system. And I think it's the same with ATO on the Victoria line as well, and Central line's the same. They've got to do their checks, and if they fail their checks, they just trundle back to the depot, and people say, "Oh, there's one train cancelled." Whereas with an engineer's train, it's on the railway. If that doesn't work, you've now got a significant delay. I think the problem specifically, Damien, on the first was to do with trains lost TBTC. I think the second train lost it big time. The third train maybe didn't even enter. And then you've got to go in slow speeds, like applying the rule. And we just thought, get them off the railway. And at the end, we lost the will to live at Neasden because we ended up with a conflict avoidance zone, which is there to protect all train movements in the area from each other. And no one could really figure out why it happened and how to get the train off the railway. And conflict avoidance zones are tricky, especially when you're new. We're also talking about Neasden service control that are quite experienced, and the Met line will be involved. And although they only control up to Finchley Road, they're less experienced. I think that's hopefully in a nutshell, quite a long nutshell.
It's interesting because we don't have quite the same problems on the mainline railway, but you can rest assured that every time there's a fringe between signalling systems, when we design it and commissioning it, that's where the problem is. ERTMS, we've got similar problems to what you're describing there. So it's horrendously complicated these days.
There are actually 2 kind of hands up. Can I invite Peter Starling to speak?
Hi there. Yeah, I was wondering with the automatic train operation, what happens with leaves on the line, where you have to have gentler sort of acceleration and braking, how it can accommodate that?
I can't actually honestly answer that question, but I think where I think that would sit would be within the train itself, because the train knows where it is. It has wheel slip detection. It has all sorts of other kit on it that can give it dead reckoning. So the train itself knows if there's a problem with leaves on the line, if it's slipping. We haven't got train detection in the rails now, so that problem has gone away. It's just really about greasy rails and being able to stop in the right place, and knowing the state of the rail under the wheels, which the train can detect. So I don't think I can quite answer your question, but I know there's something around that.
So I can help if I can add a little bit to it. So we have a risk. There's a risk on us because, yes, the train knows where it is, the signalling system knows where it is, and on CBTC it's the tags on the track, and it says to the train, I believe you're here. Where do you think you are? And the train says, yeah, I'm here. This is it, and that's fine. And the same with the track loops on TBTC. Where you go to wheel slip, and there's also tachographs on the wheels which recognise how fast the train's going, how far it's going. When the train slips, it's an unusual condition, and it will emergency brake. And then the signalling system will say, well, I'm not really sure where you are. And so you've got to enter the system, which is just like applying the rule to automatic signals or whatever in old money. So you do have a delay, there is a risk, and what our mitigation is generally from the control centre, you apply a reduced brake rate. So the brake train slows down earlier, but a reduced brake rate.
Yeah, got you. Thank you.
Perfect. And then Daniel, can I invite you to speak as well?
Yes. First of all, thank you for the presentation. I found it, very, very helpful. But I, up until kind of mid 2019, I was working for Bombardier. At the time, we were testing the class 345s for Crossrail. I was working in a different department for signalling. I don't have a lot of knowledge about signalling, but a lot of the project problems at the time seemed to be stemming from the implementation of the CBTC and the changeover of the signalling systems along the line. I was wondering if you kind of understood in any depth, like the specific problems they were having with the CBTC system on Crossrail, and whether that any lessons have been learned from that, so that going 4 lines modernization, they can avoid the problems.
Well, I think the first of all, the class 345 trains are probably the most complicated trains in the UK, if not amongst the most complicated trains in the world, because they've got three different signalling systems on them. So they run on CBTC, as you say, through central London. They then transition at the moment onto the standard BR, AWS and TPWS system running out of Paddington until they get to Airport Junction, where they then transition into ERTMS level 2. So between the centre of London and Heathrow, you've got 3 different signalling systems. And as Martin was saying a few minutes ago, wherever you get those interfaces, potentially you've got problems. So I think I'd be right in saying that the CBT system itself within central London has actually worked quite well. I don't think there's been any significant problems with the CBTC system itself. The part of the problem was getting in there to test it, because they couldn't get the trains in at either end because of other unfinished parts of the project. Of course, they have now started test running, and they're building up mileage, and they're getting a lot of experience there. And I think I'd be right in saying that the CBTC system itself has not been too bad. But the problem happens when you're transitioning from between these different systems. And Bombardier, through one of my roles on with RSSB, have come to us many times saying, look, we need to change this because we need to tweak this, and they'll tweak it. But quite often that tweak will then have an effect on something else. So it's go round the loop again and fixing that. And in fairness, I'm not quite sure that anybody has ever done anything quite so complicated as what is trying to be done on Crossrail. So it's no wonder there are problems, unfortunately. I mean, you don't like there to be problems, and you like to think as engineers we can work through them all before they happen. But it's been a challenge for sure.
Okay, thank you.
I mean, there's minor things like the fact the CBT system. I can't say that, can I? It works in kilometres an hour. You come out of Paddington onto the mainline railway and you're in miles per hour. You then go into Heathrow and you're in kilometres an hour again because you're on CBTC on ERTMS. So just converting from kilometres to an hour to miles to hour and back to kilometres per hour again, that in itself, how do you display that to the driver? How do you make sure that the systems are handling that correctly? So a lot of stuff around speed has been a problem.
Okay. Yeah, thank you. Yeah, I feel like I understand it a little bit better now.
Oh, well, if you need to know any more, I mean, let me know and I'll see if I can answer it. If not, I'll find out from somewhere.
Okay. Yeah. Cheers. Thank you.
Yeah, okay.
Thanks, Daniel. Over to you then, Damo.
All right, so I'm just conscious that we've got John Lambert's call in 20 minutes. So thank you very much, Ian. That was a very, very good presentation. And if anyone wants to ask any further questions, if you email me, I can pass them on to Ian, or I can send you Ian's details himself.
Yep, sure.
So not a problem. But again, thank you very much. It was very interesting. So one of the reasons we did pull the signal in knowledge sharing session together is because we've got a separate work stream in ITT called the Discovery Team, and we're just trying to increase the appreciation for the signal and discipline, if you like. So it's very good. Thank you very much again. Yeah.
Okay, pleasure.
So the next one, which will be next month, will be Amar Rashid, and he's talking about complex logistics in London town and a complex city. So we're looking forward to that. And as I said, if anyone has any ideas or any thing they want to share or any questions we want to address, Ian, please get in contact with me and I will pass that on. So thank you very much for joining. I hope you all found it as interesting as me, and have a great day.
Cheers now.
Cheers both. Thank you.
Thank you.
Thank you.
Thank you.